Okay, I think it's probably a good time to start. Welcome everybody. Welcome to an AI Tech Talk. I am Carl Fieser, AI evangelist for Arm, and we're joined this morning or afternoon or evening, depending wherever you are, by Dr. Nitin Gupta, VP of Product and one of the founders at Dori.AI. So welcome everyone. Quick housekeeping, any questions you want to ask during the presentation, feel free to ask in the Q&A. I'll be watching that. At the end, we'll have some more time for Dr. Nitin Gupta to answer more questions. Next, in 2 weeks, we would normally have another AI Tech Talk, but we will not because the AI Developer Summit, the Dev Summit, will be happening. Feel free to sign up for that, though. There's lots of other things happening. And with all of that, I will leave it to you, Dr. Nitin Gupta. Thank you so much for joining us this morning. And you're muted, by the way.
Thank you.
No problem.
Welcome, everyone. Really appreciate your time. You taking the time here to join this Tech Talk. Really pleased to be here and be partnering with Arm on this virtual series here. Just a quick overview of the schedule of these upcoming talks. Today, I'll be talking on behalf of Dori.AI about how we reduce AI bias within synthetic data for edge applications. Coming up in October, the next talk will be given by Arm, where they'll be talking about optimizing power performance for machine learning at the edge. So you get an overview of sort of how to deploy these models. And then our friends at Deep Light will be giving the next talk, where they'll be talking about making deep neural nets faster, smaller, and more energy efficient on low power hardware, such as ARM processors. So a little bit about myself, a little background. I'm the VP in product and co-founder at Dori.AI. Prior to this, I was leading a number of computer vision efforts in Google's AR/VR group, where we launched some of the world's first 6-dot VR and AR headsets, which included a number of Qualcomm and ARM-based processors. I spearheaded a number of software efforts also at Pebble, where I led some graphics work on our smartwatches, as well as architected some of Qualcomm's next generation software architecture. At Dori, I lead the product team, where we provide enterprises with a full of computer vision applications. If you look at the way deep learning and computer vision has evolved over the last few years, we're starting to see an explosion of images and videos being generated by various sources. And this has opened the door for millions of computer vision use cases across a range of different models. We've seen computer vision being applied across all industries within embedded intelligent cameras, mobile devices, cloud applications, and even various hybrid scenarios. And we're starting to see a rapid use of object tracking, facial recognition, and action and gesture recognition being applied to the retail, manufacturing, smart city, and many other industries. So what are we talking about today? Today's topic of discussion is primarily about how to leverage synthetic data to remove data and model bias across your applications. Many of you have faced these challenges when building computer vision applications or other ML applications where the model you trained appeared to have a balanced data set going in, but when it came out, the model that actually failed to properly predict many things or misclassified various people or objects. Just today, an article came out on TechCrunch identifying the limitation of some video conferencing applications that are trying to apply various backgrounds behind you, resulting in you disappearing or your entire body going missing. I myself have experienced this a number of times when trying to do video conferencing with my family and friends, and I've seen them disappear altogether. I felt like I was talking to a wall at times, but it just goes to show you the serious impact and side effects of putting out ML models that provide a really cool feature, but could easily cause some serious damage or to your reputation or even harm to various individuals. Rest assured today, I won't be applying any ghosting effects or backgrounds on today's call. Perhaps somebody in the audience is listening today and will hopefully work on producing an unbiased data set that will resolve a lot of these issues. But that being said, the problem of data bias is not just a singular issue, and it's not confined to just open source data sets. You have to put the problem into context of how you're actually going to build and deploy these models. So even though the data is important, just as important is also the pipeline you use. And so you need to really have a proper workflow that can leverage the techniques like synthetic data generation to properly ensure both data and model bias are removed. And I'll be talking today about how these two items are different and the way that you measure them are also different. And lastly, I'll go into how bias can be introduced even after you successfully trained an unbiased model. We'll be talking about some of the nuances of deploying these models to the edge and how that deployment may actually reintroduce some errors or even bias. So what is synthetic data generation? Synthetic data generation is the process of artificially generating data to meet the needs or conditions that are not available in existing data sets. What that means is you're trying to compensate for a lack of data that you don't have access to or unable to obtain. There are two primary techniques or types of synthetic data generation, fully synthetic data and partially synthetic data. Fully synthetic data generation involves completely simulating or generating data from scratch without any specific existing data being used. Essentially, you're taking a seed that is then used to grow that data into a viable data set. Partially synthetic data generation generally involves manipulating data that already exists by way of transformations or feeding that data to various ML algorithms. And I'll be going into what some of those techniques are in the subsequent slides. So why is it necessary to even have synthetic data as part of your standard ML workflow? The answer is as simple as the example I just gave to you earlier about the video conferencing. You may not have the data that you require to properly handle all the use cases or corner cases you are building an application for. Synthetic data generation allows you to fill these gaps by generating missing or non-existent data. It also allows you to account for objects or scenes that may be occluded or obstructed by other objects. For example, if you're trying to track a person across the screen, many times various objects may get in the way of you being able to detect that person. And if you have a real-time ML model deployed where you're trying to do sub-second tracking of a person or an object, for example, in autonomous vehicles, you need to be very sure that you handle those cases where those people or objects disappear from view because of these occlusions. You also need to handle various cases with different camera angles or conditions. Oftentimes, you only have data from a certain camera angle, but when you go to deploy your model in a different room or different perspective, you see that model miserably fails, and you end up getting a lot of false positives or false negatives. And this is because the model hasn't been trained to handle such situations. Many of us had to learn this the hard way, and we've realized that data is the key to success. You have to be able to account for various lighting conditions, environmental conditions, and even motion blur. And applying various augmentation techniques to handle the variety of scenarios will be necessary if you don't have immediate access to the right situational data. Now, I say situational data because many of you may be thinking I can just start off a POC with a company and just collect data after I deploy. This is absolutely necessary, as you can't just deploy once and forget. But you may quickly realize that what you deployed also doesn't work 90% of the time. There are definitely going to be situations that you cannot predict or will not have encountered in your training data sets. So it's absolutely vital to do what you can upfront to account for these limitations of data so that you are successful in the long run as well. Now, we've seen synthetic data generation already being applied and used in a number of industry applications. A few examples that I want to highlight here are manufacturing, automotive, and smart city industries. Within manufacturing, we're seeing enterprises use synthetic data to simulate part defects such as scratches, dents, or discoloration. Most successful manufacturers have spent a lot of time and money perfecting their manufacturing processes, and as such, the amount of negative data they have is actually very limited, meaning that they have very few cases where products are actually going to be defective. So your sample data set size is going to be heavily skewed towards the positive or near perfect products. This means also that your model will be skewed potentially towards a positive or a non-defect prediction rather than a negative or a defect prediction. And this can be obviously a serious problem because you don't have that data. Now, many have tried to solve this by applying a differential analysis and say that a defect is anything beyond a certain threshold. Meaning if it's anything but perfect, then if it passes that certain threshold, then we just automatically mark that as defects. But that could also lead to a number of false positives as well. And this really doesn't work in many situations, but there are definitely cases where it can. In the autonomous vehicle market, self-driving car companies have had to rely heavily on simulated scenes and imagery. They simply just cannot collect enough data by just driving around cars with video cameras on the top. There are just too many unpredictable and rare conditions that have to be accounted for, and it can't be done through just simple data collection. Synthetic data generation is an absolute necessity before even deploying any model for these types of applications. And similarly, for smart city use cases where surveyors and city planners are trying to use this data, they are trying to actually do various zoning or construction surveys where they're applying various filters to this imagery, and then they can generate models that can actually do area reconstruction or even topographical analysis. So let's dive into what some of those techniques are of various synthetic data generation. There are two main techniques that I want to highlight today. The first being data augmentation. This involves manipulating existing data sets through various methods. These include applying color spaces, thresholding, morphological operations, and filtering. Within color space, there are a number of color spaces that could be applied. You generally use this technique to simulate various lighting or environmental conditions where you can apply various colorizations to the background or to various parts of the video. Thresholding allows you to apply various filters to the image. We've actually seen this even used to sharpen various imageries to get a higher level of contrast for readability and even various OCR applications. Morphological operations is generally the most common data augmentation techniques, where you can apply techniques such as rotation, translation, flipping, and resizing. And this is a quick and easy way to really enhance your data set and expand it dramatically for various permutations to account for also various angles, perspectives, and even poses of various objects or people. And we've seen this also being used a lot with respect to semantic segmentation applications, where you can segment out various objects, rotate it, translate it, etc., and then feed that back into the actual training data sets. And then finally, you can apply various filtering techniques to deal with things such as motion blur. A lot of times you may have various video feeds that are coming in, and in order to properly track that person, you may not actually have the data that is properly blurred out. And so if you want to actually track across frames, you're going to definitely get that motion blur. And so it's very important that you also include both the non-blurred version of, say, that person as well as the blurred version, so that if you don't have, for example, a high frame rate or you have a low resolution camera, be able to account for those situations. Now, recently, over the last 5 years, we've seen a huge advancement in the area of GAN, or generative adversarial networks, where data is used to train a model to artificially generate new data. This technique involves training a pair of generator and discriminator models until the data has reached a point where even the human eye can't actually detect what is real and what is fake. And we've seen a large number of algorithms generated over the last few years that have come out of the research community stemming from Goodfellow's seminal work in 2014. Since then, we've seen a number of algorithms coming for image blending, where two images can be blended together to create a new scene. Substitution algorithms, where we take one person with glasses, subtract out the person, and substitute a new person. Image-to-image translation, which is also similar to the blending technique, where we actually take the properties of one image and apply it to another, so you can actually simulate various scenarios. And we've seen this actually applied a lot, especially when you're trying to do day and night transformations. So if you've actually only got data for during the daytime, and you actually want to also do various detections at night, you can apply this technique to basically take that training data that you have, apply these filters, and then generate even data that can simulate a night scenario as well. We've seen this actually used a lot in security applications, where security cameras are very good at detecting when situations when it's daytime, but then in the night they fail miserably just because there isn't enough data available. We've also seen algorithms come about that are able to fill the gaps between missing video frames. This can be a very useful technique when you either have a low frame rate coming in or trying to detect various SOPs that people or motions of people. We've seen also super resolution algorithms enhance existing imagery where you may actually have a low resolution image. The purpose of the super resolution is to really get that fidelity so that when you actually train the model, you actually train it for the object or person that you're trying to detect. And we've also seen complete scene generation being used from just taking a semantic mask, where, and this has been especially used in automotive applications and the autonomous vehicles, where they can basically create a number of semantic masks for various scenes throughout, say, the streets or various road conditions, and then be able to completely simulate that data so that the model can be trained for various cars, various people, various situational data. Another very interesting application is the use of face rotation, where a lot of times when you're photographing people or various video cameras are trying to capture various people in different poses, you may not actually have their entire face. And so this is a very useful algorithm where you can actually fill in those perspective gaps. And lastly, there's a lot of huge potential actually in terms of pose generation, where you can generate various poses of people's arms or legs, where if you don't have the data for a certain, say, action that a person needs to perform, you can actually simulate that by generating various poses of a particular person. And so we found that very useful when trying to do action recognition models where you don't have the actual pose information. And so why is this really important right now? What we've seen is that there's been obviously a lot of issues lately coming in the news where various situations have occurred where models aren't able to predict various people or have mistakenly predicted people as gorillas. And so it's very important that when you actually start a project that you have the right data to begin with. Obviously, volume of data is limited in most use cases. And there are obviously a lot of edge and corner cases that you just can't capture, either because they're hard to get or situations are very rare. And this introduces a lot of imbalances in many of the data sets that are used to actually train various models. And you see that a lot in also the public models and public data sets that are there in the open source. The second also major concern that's really hit the industry is the issue of privacy. More and more people are becoming much more protective of their data, and especially when it comes to PII information. And so being able to collect data that is representative as well as able to predict the scenarios that you need is becoming increasingly challenging. And so the use of synthetic data is going to be quite a vital part when it actually comes to generating real world applications. In order to simulate these situations, you're going to really need to look at how synthetic data can be a common part of the workflow that you incorporate in your everyday pipelines. And it really begins with actually setting this entire pipeline up. So really the formula for success and velocity in building these applications is to actually leverage an entire end-to-end workflow where you can take advantage of these techniques, but also have the entire end-to-end feedback loop that's necessary to further improve your models. And so it begins, the way that we approach this is really in terms of a three-stage pipeline. The first stage of that pipeline is the data pipeline, where you start to collect that data and start to feed that into those various augmentation or generation techniques. This first part of that process is crucial before you even start to train your model, because as you start to collect more and more data, you're going to need to possibly apply these techniques in order to account for those various corner cases or negative use cases, and then feed that data into the annotation tools that you would be using. We've also seen it flipped the other way, where you first annotate some data and then proceed to augment and generate that data afterwards. Depending on the situation, you can apply either technique. If you annotate first, then you get those augmentations for free. that are also annotated with the same label. Once you've got that, those data sets generated, then you move into the model pipeline, where you then will start to train and optimize your models in order to see what kind of accuracy levels you're getting from those particular data sets that have been used. And this training process is quite an iterative process, as I'm sure many of you are aware. But what I want to highlight is the importance of benchmarking. Most data scientists, they have a certain data set that they use to validate the models. But as an organization, as an application developer, it's actually quite vital that you have a much larger data set that is not included in the training data set or the validation data set that you would then benchmark before you even consider deploying a model. And this is very crucial because you want to make sure that your model is not been overtrained or overfitted to any one particular data set or label. And so it is vital that you actually hold back a lot of data that is used during the benchmark phase, so that way then you can actually see if the data set that was used to train has actually accounted for some of these nuances. The other aspect that I want to highlight is that it may not just be one model that you employ. There's a very important technique called ensembling, where you may actually require multiple models in order to satisfy any given one use case. And it's possible that you may end up training different models for different data sets or different classes, and then combine the predictions into a third model, for example, where that would then take those two predictions and actually produce the event or detection that you're actually looking for in the application. And then finally, when you actually go to deploy this model, you need to make sure that you have various infrastructure and various techniques in place in order to collect that data from runtime. So when you actually deploy these models, you need to make sure that you're able to then sample that data so that it can then be fed back into both your data pipeline and your model pipeline in order to then further account for any runtime data that you may be receiving, or any use case or corner cases that you may not have trained the model for. And if there's time at the end, I'll actually walk through each of these steps and talk about how we can, what are the considerations at each of these steps along the way. So when we get into the data pipeline, there's really two main considerations that you want to look at when it comes to the data imbalance. The first is a sample bias or a class imbalance. Most sample data sets that you get are not really representative of reality. There may be either one class that has too few or one that has too many in that training data set. And so in order to account for that, you're going to need to analyze what does that label distribution actually look like. The other type of data imbalance that you may have is just the lack of negative use cases that I talked about earlier. And this is quite common in manufacturing use cases where, again, you may not have, for example, a lot of bent parts or ones that have various scratches or various colors, but these are actual possible aberrations that may come up when the manufacturing process is actually rolling out. And so in order to account for these two types of imbalances, there are various techniques that you can employ to actually analyze the data set before it's even fed into the model. And generally what you try and do is you actually do a statistical analysis of that data set to find out what does that label distribution actually look like. And it's very well possible that you may actually want to have that imbalance, and I'll actually go into why that might be the case. And so in order to sort of rebalance that data set, you need to make sure that you complement your existing data set with that additional data that needs to be synthesized. Most enterprises, again, will not have that data available or be able to give it to you. So you're going to have to then take it on yourselves to actually build in that infrastructure and tooling that's needed to create that automatically. In order to scale, you're going to need to set up that pipeline where you can generate that data automatically and then start to analyze that to see where those gaps are. What negative use cases don't you have? And as you progress with the customer, you're going to see that there's going to be more and more situations or more products, for example, that they are producing where you're going to need to feed that new data into these models so that they can continue to predict new situations, new objects, new people. And so you're going to need to have a structured pipeline in place that allows you to continue to do this analysis and then feed that into the model pipeline. And so really, in order to set that up, you need this is sort of an example of how you can actually set up that pipeline. We at Dori have separated out that into 4 main functions. The first being the data generation engine, where we can apply various GAN algorithms or various techniques to be able to generate that fully synthetic data. Second, we have a data augmentation engine where you can then take that data set, both the existing as well as any of the new data that was generated, and then apply various techniques such as rotations or translations or any sort of filtering to then simulate those various situations such as motion blur or various perspectives, various angles, etc. Subsequently, then we apply a data bias analyzer, where we then look at what does that distribution of all of those data sets look like and all those labels in order to make sure that we have a properly balanced data set before we even go into the training phase. And then we also build in the utility of actually splitting and merging various data sets. It's very possible that you may have disparate data sets coming in from different data sources or different cameras, for example, or different locations. And so it's actually very useful to create a scalable data set split and merge engine where you can then quickly put these data sets together and then feed that into your other engines. And then finally, once you've actually got that final data set, then the last part of that process is actually then feeding that into the model pipeline. Now, one thing that you need to be made aware of is that removing the data bias doesn't necessarily mean that you've actually removed the model bias. You may actually, when you actually train the model, you may find that your model actually skews still toward a particular class or a particular label. And so how do you really ensure that your model is actually unbiased even after training with an unbiased data set? The answer lies in actually analyzing it on data sets that you actually benchmark. And so you may actually have to look at what activations are present within the model predictions in order to then possibly retrain that entire model with a much more balanced data set, rather than just incrementally training on new data. And so really, you need to start to create specific data sets that are actually going to test that model and data set bias. So what we've done at Dori is actually, whenever we approach a customer, we actually segment out our data sets for various different purposes. Some of them are just ensuring mission mode execution. Some of them are actually analyzing various bias conditions. And so through that process of automating all of this analysis, we're able to much more quickly create a balanced data set that actually is not necessarily favoring one label or another. And through the analysis that we can do, we can actually extract out then which labels or which imagery are causing these biases, and apply various techniques such as gradient analysis or any pixel level analysis, which allows you to then see what exactly are the most important features that are actually causing this prediction. And so through that analysis, then you can then decide if this image is actually even worth putting in the data set or not, or is it actually causing an unfair bias towards any one prediction. And so the impact of actually doing this analysis then is that you can then avoid that sort of overconfident or misclassifying model, and then get a much more deeper understanding of exactly what contributes most to the actual predictions that you're building up. And so when you actually go into production, then you have to start to consider what are some of the challenges that you might actually face when it comes to edge deployments. Data collection is often very difficult when it comes to deploying models on the edge or on premise, and it's possible that you may not even have access to some of that information because either data is kept private or securely on a device or on a server, and so synthetic data may be your only option. And so, but one thing to definitely keep in mind is that for most edge scenarios, you end up applying various edge optimizations, such as pruning or quantization. And those techniques, although they are very great at optimizing for latency and size and performance, they may actually introduce additional biases or additional errors in your models that you may not have accounted for. And so again, I really emphasize that you need to benchmark these optimized models to make sure that on the data that you've trained with, as well as that data that you've held back, is the optimized model also performing as expected? Have you actually introduced or not introduced any of these errors in that process? And then finally, once the model is actually deployed, how do you ensure that your model hasn't drifted over time? And to make sure that there isn't actually still some inherent bias for situations that you may not have encountered during that initial data collection phase. And really the way to account for those scenarios is to continuously monitor your deployed models and start collecting those data at runtime so that you can audit that regularly and start to reintroduce that new data into that entire pipeline so that you can feed it back into both the data pipeline and the model pipeline and ensure that your models are still robust even after they've been deployed. And so it's very important that even for a deployed model that you introduce a runtime monitor that can then start to extract that data and then start to feed that automatically into that data pipeline. So your data science team or your annotators can then start to include that as part of that model upgrade process. Now at Dori, what we have done is to actually integrate that entire end-to-end workflow into a seamless computer vision pipeline. You can basically connect up any image or video data source and start to augment and generate those data sets automatically. So during that data collection phase and that data annotation phase, you can much more seamlessly create those unbiased data sets and analyze them within a single unified dashboard. We allow our customers to very quickly build and deploy these models for any use case and deploy them either on any edge or edge device, edge server, or even on the cloud on Amazon or any other cloud service. And we support all the major chipset vendors, including Arm and their optimization tools as well, so that you can then start to leverage the performance that you get from these chipsets. And as a result, also as part of that deployment, we also enable our customers to get those insights from the runtime by analyzing what those predictions are, sampling that data, and then feeding that back into the pipeline. Now, I have about 15-20 minutes left, so I'd like to actually dive in a little bit more to just give you some food for thought in terms of what some of those pipeline stages considerations are. So I'll go back to this pipeline. I'd like to just dive a little bit into each of these phases so that you start to think about what are all of those elements that you may need to consider when actually deploying such applications. Again, for the data pipeline, it really consists of three main phases. The first being that data connection phase, where you actually start to collect that data and ingest that into your pipeline. The second being the annotation, where you actually will then start to establish that ground truth. And then finally, your augmentation or synthetic data generation process. So when connecting various data sources, you'll definitely want to start to consider what types of formats that you want to support, whether it be various image formats or various MP4 or AVI video formats. When creating a production pipeline, our recommendation is to stick to a single format. So that way then all of your tooling internally becomes much more seamless. So it's maybe necessary to create just some simple converters at the ingest phase so that you can then just deal with one simple pipeline to start with. Also, you want to consider what type of resolution that you're ingesting as well, because obviously the higher the resolution, the larger the amount of size of data that you have to then manage and store. Because obviously for large data applications, you're going to probably end up leveraging cloud storage for that. and those data storage costs can actually add up. Third thing to consider is also the frame rate. For many applications, you don't actually need a high frame rate of like 30 or 60 FPS. You can actually do well with even just a single frame rate, 1 FPS frame rate for most applications. And so definitely take that into consideration when actually setting up your ingestion pipeline, and as well as what connectors you need to the various devices or DVRs or IP cameras. And most IP cameras, most DVRs, they can actually be configured to set up those substreams automatically to be of lower resolution or lower bandwidth or lower frame rates. So definitely look into what hardware is actually being connected into your pipeline, and then look at how you can optimize even those settings, because it'll then overall help your overall performance of that pipeline. Second, on the annotation side of things, definitely look at what type of noise is actually present in some of these images or videos that you're ingesting. You may have to annotate things differently based on various occlusions or various perspectives. Again, these are some of the considerations that where synthetic data generation can definitely help in that process in terms of being able to also generate some of that missing data. And then obviously in terms of the synthetic data generation, these techniques are a number of these ones I just spoke about. You can apply various GAN algorithms or various transformations. But again, we recommend that you first start out with simple techniques such as CV transformations, like translations and rotations. That may be sufficient for you to actually get a high level of accuracy initially to start with, and then proceed to actually more sophisticated techniques depending on the actual application. Within the model pipeline, we kind of break this down into sort of 6 main steps here. Obviously, the first step being selecting the specific model for the particular use case that you're implementing, followed by actually training that model for the custom data sets that you have. Validation is obviously a big part of that training process, and typically already integrated into various tools like TensorFlow. The fourth phase of that process is the actual optimization phase, where you can then start to leverage tools like Arm's NN library or other optimization techniques like pruning or quantization, where you can then start to take advantage of the hardware acceleration that's being built into these chipsets. But then the fifth stage is one of the most important phases, where you need to start to benchmark your model for various accuracy as well as system performance. It's not sufficient just to take your model from the data science team and start to deploy that. It may be completely an unviable model if it doesn't even meet the performance constraints or the system constraints. And so it's very important to ensure that you have that transparency there. And then the sixth phase of that process is the ensembling process, which I talked about, where you may actually need multiple models in order to satisfy a given use case. And so when it comes to model selection, obviously, a number of things to consider in terms of both the type of model, but also whether you create a fully custom model or just leverage a pre-trained model and do transfer learning. For many computer vision use cases, the technology has reached a point where transfer learning is actually a great place to start and can satisfy a lot of simple use cases. And you can add a number of image pre-processing and post-processing logic to that in order to get the data into a format that your model can actually predict on. And so some of those techniques that I mentioned in the data ingestion phase also apply even when you're actually building up your model pipeline, where you may need to downsample some of the imagery or decrease some of that resolution. All of that would be part of your pre-processing logic. And then finally, on the post-processing side, a raw prediction may not be what you actually need in order to recognize, say, an action or recognize the motion of an object. And so there may be certain post-processing logic that you apply after the model predicts to actually detect an event that actually occurred, like somebody entering a room or an object like a piece of equipment in motion, right? And so you definitely need to take that into consideration as you're starting to build your model pipeline. And then when you actually finally go to train your model, you may actually need to validate it in the context of that entire pipeline. And so you need to just make sure that you don't train just that model in isolation of without looking at the pre-processing and post-processing logic. Now, when it comes to actually training these models, one thing that is often not considered by most data scientists is the cost of training. It can actually be very expensive to keep these GPU cloud instances up and running for extended periods of time. And so definitely consult with your product manager as far as what the budget is for training, because that will be a big consideration when it comes to actually whether you take on a particular customer or not. The cost of training alone could make or break a project because of the amount of data that you may need to actually deal with, or the amount of training cycles that you may have to go through in order to get even a viable solution out the door. And so definitely techniques such as optimization could also help in terms of optimizing that training process and that performance as well. So definitely look at what types of techniques you can apply with respect to simple techniques like quantization and pruning, but also looking at it from a system perspective. Take a look at what tools ARM provides, take a look at what your chipset vendors provide, and see how you can actually leverage that in order to actually reduce some of those latencies and get the frame rates that you need to detect those scenarios or SOPs that you're looking for. And then finally, when you're actually looking at a solution from before you even start to build out your model, definitely look at how you can actually break that use case down into multiple models, because it may be the case that, for example, if you're just trying to look at a moving violation of a person, there may be a number of different models that you need to employ. For example, you may need to first detect the person, then detect the motion that they're and direction in which they're going, as well as whether they're reaching a certain boundary. For example, in a security or surveillance use case, you may need to detect when a person goes in and out of a particular hazard zone. So that may be a combination of multiple models, but also various post-processing logic that you may need to apply. And so, and again, what also needs to be considered is the overall latency and throughput of that ensemble or chain, as well as the cost, because obviously if you have more than one model, you're going to need to have more hardware to run that. And so there's both the cost in terms of the system performance, but also even if you're running this on the cloud, then spinning up multiple instances in order to service those models may be a make or break. And then finally, on the deployment side, again, we break this down into a number of steps, where the first step being determining where you actually want to deploy this model. This model could either be deployed on the cloud or on an edge server or even on an edge device. Start to look at what kind of predictions you actually need. If it's an edge deployment, what predictions do you need absolutely at the edge, which require a low latency or for various other concerns like privacy, and what can you do on the cloud? Obviously, with cloud, you have much more hardware, much more compute available. So any long-term predictions or non-real-time predictions in general, if you have the ability to do it on the cloud, then that's the recommended approach. And then once your inferences engines are actually up and running, you need to just figure out also how you're going to feed that to the actual application or business logic. An application is not just a model. An application has an entire set of infrastructure around it, including databases, various visualizations, possibly various API connectors to third-party tools. These are all things that you need to actually think about when actually building this entire solution, because that model may be just one piece of the puzzle. You need to set up an entire infrastructure in order to support the application, and what do those interfaces look like? Within Dori, we've actually standardized some of those interfaces, so it makes it much more easy to actually build out these applications rapidly and not have to then worry about setting up all those databases, setting up all those APIs. We provide that automatically for you. And then finally, once those models are deployed, you need to then set up those metrics and those data collection agents, so that way then you can start to feed that back into your annotation and training pipeline. And so when it comes to deploying those models, obviously Docker and Kubernetes has become sort of the go-to for actually scaling up your model pipelines. But definitely look at sort of what type of what your quality of services that you want to provide to your customers and what that experience looks like, so that you can properly balance that scale appropriately. The other aspect is, how are you going to do device management? You need to, if you're dealing with, say, a large-scale video deployment where you have a number of cameras coming in, you're going to need an entire VMS system in order to manage all of those devices. So how do you set that up? Within Dori, we've actually got our own internal proprietary VMS system that allows any camera to be very quickly attached to our pipeline. And then within a matter of minutes, we can just set up all of those models and all of those metrics, and then be able to give you those insights right away. And so in order to set that entire pipeline up, it can be quite a daunting task. And when it comes to actually integrating these into the applications, you need to look at, how are you going to consume these results? Is it going to be real time, or is it going to be offline? Where do you store these predictions? Do you store it in a local database, or stream it up to the cloud? If it's up to the cloud, then you need to make sure that you have various APIs available, so that you can then put those results actually into the appropriate database. And then how are you going to actually then visualize that data, or feed that into the application? Are you using a BI tool like Tableau to actually visualize all those results, or do you have a custom React dashboard? We at Dori can help you with those decisions, and actually provide you a lot of the templates that are actually needed to connect to some of these tools. On the monitoring side, again, how do you set up that sampling pipeline? What data do you need to sample? How often do you need to sample it? Are there any data storage considerations when you're actually sampling that data? If it's on the edge, how much data can you store? Obviously, you're limited by the amount of storage that's available on that particular device. So you need to start to think about, how do you sample that data, and then how do you upload that data on a regular basis, so that way then it can actually be used by your data science team. And then also, how do you analyze the actual system performance? It's important to also make sure that your models aren't taking too much of the compute away from those edge devices, or even on the cloud. And so how do you deal with that, as well as how do you merge all of those data streams that are coming in? If you're deploying a large-scale deployment of hundreds or even thousands of cameras, how do you manage all of those incoming data streams? How do you sample that data? Do you need all of that data? These are all things that you need to start to look at when you actually deploy these solutions. And then finally, when it comes to actually analyzing and retraining those models, you need to have a process in place to be able to analyze whether those models are actually drifting with respect to what you actually benchmarked in the development phase. And there may be certain biases that you may encounter where, for example, if you're deploying a model that is detecting something that is very localized to a particular country or region of the world, you may realize that if you try to deploy the same model into a different part of the world, that the model completely behaves differently. And so these are things that you're going to need to start to consider as you start to scale, because it's very possible that you may only have certain access to data in this region and not others, or even time of day may be an issue. In certain times of day, models may predict much more better than others, like, for example, in terms of day versus night. And so you need to be able to detect those anomalies and then create those active learning loops, so that you can then feed all of that data back into your overall pipeline. So that concludes our talk for today. I really hope that gave you a good flavor of what are some of the considerations that you need to have when actually creating these models and these data sets, and also what is the kind of pipeline that you may require as you start to build out these end-to-end applications. Lastly, I just want to highlight that on October 6th to the 8th, Arm is holding the DevSummit, so definitely do look into signing up for that. There'll be some really interesting talks and interesting information shared at that summit as well. With that said, I'll hand that over back to the Arm team.
Awesome. Thank you so much. That was really informative. It seems like you're kind of offering the whole package in terms of training and helping with the synthetic data side, and then optimizing and deploying, which is like, that entire workflow is extremely complicated. So it's really nice to see that you're kind of fitting in the gaps all along the way. Are there any questions from anybody attending? I know I have some questions. Anybody? You can raise your hand and I can unmute you, or you can just type it in the Q&A, or feel free to just chat it if anybody has any questions. I did have a few. So you at the end you started talking about drifting data, drifting models, and like what things could you recommend, and how can Dori help in terms of either fixing with this drift, or if you're coming across new data in the field that you didn't account for when training your model, like how can you fix these things without having to retrain the entire model completely, and what kind of tools are there for people's disposal?
Excellent question. So when it comes to model drift in the field, we've encountered this a number of times. There's definitely scenarios where a model may predict a false positive or even a false negative. False negative being the harder scenario where you don't even detect anything at all. And so one of the techniques that we've employed is actually employing multiple models, where the secondary model is not actually the core prediction that you're trying to do. It may be just a simple object detection. And so what we've done is, for example, we have an action recognition model that's been deployed that one uses this object detection model to detect some of the basic objects, like for example, people and the asset that they're interacting with, and that feeds into the action recognition model. Now, we've encountered situations where that action is not detected at all. And so what we do in that scenario is we go back to the raw predictions that the object detection model has detected, and then start to see what were those raw frame by frame predictions. Because when it comes to especially a false negative prediction, if you're just solely looking at the action recognition model, you have no data to go by to say that the action was missed. You just didn't predict it at all, so the model will just keep going on its way. But the object detection model that's supporting that action recognition model may actually detect various things that you filter out when you're doing the action recognition, but don't actually. So it's extra meta information that you can then leverage to see possibly a false negative happened at this frame in the video. And so what we do is at Dori, we basically automatically extract that information on a sample basis, where we can set up various heuristics to say, okay, sample whenever you don't have an action detected, but you have a specific object that is most likely going to cause an action to be detected. And so that way, then we can set up these rules automatically. So that way, then you start to sample on those anomalies. And then later, our data science team then has access to those individual frames or even video snippets that we extract from the runtime data. We've also set up a video annotation pipeline where on that runtime data, we're automatically extracting those detections, both the action and the individual objects, and then automatically creating those annotated snippets. So you can then see those individual detections. Your data science team can then immediately hone in on what those predictions were and how to then shortcut that actual analysis cycle, because the analysis cycle itself can take many, many hours of time just to figure out what data to even look at. And so with this tooling that we put in place, you short circuit that analysis time, and then you can immediately feed all of those annotations directly into your training cycle. So you don't even need to necessarily re-annotate. You just need to audit to see if those annotations are already correct or not. We can then immediately feed that back into the training pipeline. And then when it comes to actually generating synthetic data out of that, then we can also feed all of that data that you're collecting at runtime directly into our synthetic data generation engine, and then be able to create those new data sets for you automatically.
Yeah, that sounds extremely helpful. Yeah, that's always a constant problem. Like, yeah. I think a lot of work is done in terms of like before deployment work, in terms of training a model, getting it ready, and then it's kind of a set it and forget it mentality. It's nice to know that like you're kind of working on keeping those models up to date and working with new existing data streams, and especially hitting those like false negatives, because those are kind of where ML falls into holes. There is a question from Mehul Gandhi. Does Dori.AI provide the model optimizations for edge devices such as MCUs?
Yes, so we basically tied into all the major chipset vendor tools. We leverage their existing SDKs that they provided and the optimizations that they have. So we have various API connectors that actually are built into the process. So one of the actual phases of our dashboard is to actually go into that optimization. So you can then select, okay, what is your hardware? What type of techniques you want? What are your thresholds for pruning or quantization? And so you can select all of those parameters, and then what we've done is sort of created that common translation layer so that depending on what hardware that you select, we can actually then feed it directly into those individual chipset tools.
Excellent. You did mention something about using multiple models at the same time for a lot of the error correction you're doing. Is there any kind of power limitations specifically around the MCUs where you need a certain level of power for the models you're running plus anything else you're trying to do in order to catch these kind of fail states?
Well, when it comes to measuring, like, say, power, for example, again, this is something that you're going to have to account for when you benchmark before you even deploy. So if you're putting together, for example, multiple models, one, there's the issue of scheduling, right? Because if it's on an MCU, obviously CPU is going to be limited, and the hardware availability or access to the CPU is going to be limited. So you're going to have to look at various other techniques to account for the amount of horsepower or current that you actually draw for these various models. And so in order to address that, what we also look at is not trying to run these models at such a high frame rate. We often downsample the image before it even gets into the MCU itself. And so, for example, like I mentioned, even at the source of the camera, you can start to downsample the resolution, the frame rates, and even start to employ even data capture facilities that even the hardware itself, the camera hardware may have itself. So there may be certain features that these IP cameras have where they only turn on when they actually detect motion, right? So right away, you're not actually burning CPU cycles on frames that you don't even care about. You're only actually kicking off these ML predictions when there actually is motion. So that's one part of it. The other part of it is if you're ensembling together a couple of models for prediction, then you may actually optimize these models differently and independently depending on what the actual prediction is. So you may actually only kick off, for example, you may do the object detection very regularly, but then only kick off the action recognition model when you see a particular object. And so as part of that ensembling process, you would actually stick in some logic between your object detection model and your action recognition model to filter out some of that noise. So that way then you're chaining together a number of, the models in a way that also optimizes the amount of compute that you need for that entire pipeline.
Awesome. No, thank you for that. I think we have time for one more question. I know I have one. If there's any other questions from anyone attending, raise your hand, throw it in the Q&A. If not, I have a question. So I'm a big fan of open source. Given that Dori you're building a product, where is it better to use open source, or like where do you draw the lines between the open source, which is very popular, especially when it comes to machine learning, versus using something like Dori, and like where do you find or any kind of other proprietary solutions, like where do you find the balance between these things, and what you recommend?
Yeah, that's an excellent question. We are all for open source as well. I mean, I think it's a great place to start. And within our platform, we also do give access to a lot of these open source models, open source data sets as well. Because obviously just starting out, you don't have access to certain data. And if you're trying to prove yourself as a viable solution to a customer, you may only have the open source to start with. But when it comes to actually productizing a model, you're going to need to obviously use data sets that are provided by the customer. Every solution is going to be a custom solution to some degree. So the open source data sets can only go so far. They can I mean, a lot of these models have reached a level of maturity, especially YOLO and a few others, where that is an excellent place to start as your base model, but then start to use techniques like transfer learning to start to improve those models on those customer data sets. So it's a great idea to start to segment out even your models that are for a specific use case as a base model that you can then leverage for other customers. And then just have to just do simple retraining of that specific use case model for their specific scenarios. And when it comes to actually tooling, I would say if you're setting up a pipeline like what we have done at Dori, you want to you're going to end up leveraging a mix of both open source and proprietary solutions. There is quite a beast, obviously, that is required in order to create a seamless pipeline like we have. And it's going to be a mix of open source and your own custom pipeline. And so in terms of trying to find that balance, obviously, the recommended approach is to build last. First, see what you can leverage that's out there in order to quickly get a pipeline up. But then in order to really scale, there's obviously a lot of different automation that you're going to need to put in place. And that's where Dori can really help accelerate that process, really enabling especially the application developers to focus on what they're really good at, and that is really at the application layer. And so within Dori, what we've done is actually enable non-data scientists to build these applications without actually even having a deep understanding of how these ML algorithms or what some of these metrics are. So we've created an abstraction such that even a product manager or anybody who's at the business level can actually use our platform to build out these applications very, very quickly.
Awesome. Thank you so much. I think that's all we have time for. Do you have any kind of closing remarks or anything you want to leave everybody with?
Once again, I think it's really important to look at these applications at a holistic level. It's not good enough to just look at your piece of the puzzle. If you're in an organization where you're part of a team that's trying to build out an application, really look at how your piece also ties with all the other pieces, because when it comes to especially this issue of data bias, it does affect every piece of that pipeline. And so it's really important to make sure that you have a structured pipeline that allows you to analyze how well these models are performing at each phase of that process. And at Dori, we're more than happy to have a conversation with you to help you get that kick-started.
Awesome. Thank you so much. Thank you for that presentation. Everyone online, definitely check out Dori.AI and also check out the DevSummit. It's 2 weeks away, still time to register. I still think so there's some room in some of the workshops. And thank you so much. Bye, everyone.
Yeah, thank you.